Hello, I'm Igbek, and I'm today going to present our paper, MININODE, Reducing the Attack Surface of Node.js Applications. The co-author of this paper is Alexander Kapravelis from North Carolina State University. First of all, what is Node.js? Node.js is JavaScript runtime engine based on Chrome's V8 and Lubuf library to provide the built-in OS functionalities such as file systems, network access, and so on. When users install the Node.js, it usually comes with its own package manager called Npm, but the developers can use also additional Yarn or other different package managers. Initially, when the Node.js was developed, it was using the model system Commonjs convention, but later on they started to switching to the ES6 module system. However, because it was developed long ago, the majority of the packages are still based on Commonjs. So first of all, what is Node Package Manager, or shortly NPM? NPM is the largest package manager by number of hosted packages. So as of July 19th, 2020, it was hosting more than 1.3 million packages. Majority of the packages are simple packages, which means they consist of only one function, and NPM by default installs dependencies transitively, which means if the application is dependent on package A and package B, but those depends depend on other packages, it will install all other packages. Also know that it will install the package B different versions. So basically, if package A is depend on other version of the package B, so the both version 1 and version 2 of the package B will be installed. Commonjs module system, or we should say it's sort of like a convention. First of all, the Commonjs is not standard module system, but sort of like a workaround. JavaScript in 2009, when the Node.js was developed, didn't have any kind of syntax to implement the modules, and the developers come up with the Commonjs convention. In the Commonjs conventions, modules use the exports object to export and require function to import other modules. So on the right-hand side, you can see the example of the module B, which is exporting two functions, greeting and goodbye, and module A, which is importing the module B using the require function and using only the greeting. So theoretically, you can reduce or remove the goodbye function, and it will not break the initial behavior of the application. And under hood, the require wraps the module's code to isolate its scope. So this is the example of the or syntax of the require function wrapper. So our problem statement is that the Node.js applications usually suffer from dependency explosion because of the transitive dependency installations. So here you can see the example of the Express, one of the popular package called Express, and as you can see, it has a lot of dependencies. So when you're installing Express, so it will actually install all the other dependencies that you can see from the graph. So some popular packages may depend on 200 other packages, some of which are outdated and or vulnerable. All applications by default, and also another problem is that all applications by default have access to built-in modules such as file systems, networking, and so on. In our threat model, the attacker can execute arbitrary code due to vulnerability inside Node.js applications, and thus can load unused modules to make it much more easier to exploit the application. There are general two ways to load the unused modules. First is directly manipulating the require function, and the second one is indirectly manipulating the require function. For the simplicity, we here present the directly manipulating of the require functions. As you can see, the attacker can can modify the header value for the encoder, and then thus can pass any kind of value he wants, thus loading the maybe unused or external some other modules. So during the development of the MININODE, we come across with the two main challenges. So we categorize them as expert-related challenges and import-related challenges. Expert-related challenges group together challenges related to how module exports its functionalities. So in this example, you can see that instead of directly manipulating the exports object, the module is exporting using its alias. And import-related challenges groups together challenges related to how module imports other modules and uses other modules functionality. So here the example of passing the variable instead of the string to the require functions. So to be able to detect that server.js is used, we should be able to detect or find the value of the mode variable. So expert-related challenges affects how well we can reduce the attack surface of the applications. Failure to resolve usually will lead to under reductions. So if we fail to remove some of the functions, basically, we may end up with more code which is unused, and our application will be bloated. On the other hand, import-related challenges affects how well we can detect the use functionality of each module, and failure to resolve will lead to over reductions. So if we fail to detect which functions are used, we may accidentally remove them, which may break the initial behavior of the application. So on the right hand side, you can see the example of the one of the examples that we saw in the wild. We call this example parent-child invisible relationship. So in this case, as you can see, the parent, which is importing the child.js and then extending it. So basically introduce a new function greeting that parents, and the child module is actually using this greeting parent function, which was defined inside the parent.js without ever requiring the parent.js inside of it. So this is like unintuitive one of the examples, the challenge that we need to resolve to implement our solution MININODE. On this slide, you can see the overview of the MININODE architecture. MININODE consists of 5 different parts: parser, value binding, load dependency builder, call graph builder, and reducer. MININODE also supports 2 modes of reductions: coarse grain and fine grain. During the coarse grain reductions, we don't run the call graph builder because the coarse grain reduction basically is file level reduction when we remove the unused module itself, while for the fine grain reductions, we also, addition to the load dependency builder, we also go to the fourth step, which is call graph builder. When we, in addition to the removing the unused modules, we also reduce the functionality of the used modules. And at the end, we produce the reduced version of the application. On the next slides, we will be discussing in more details each of these steps. The parser is the most obvious and the easiest, the first step. The parser basically parses all JavaScript files into abstract syntax tree using the Experiment. The second step is value binding. During the value binding, we try to statically resolve the values of interesting variables, such as else of core objects, such as exports, module, require, and variables used as a parameter to require functions, and variables used as exports object property. During the load dependency builder, we construct the file level dependency graph by resolving the return value of require function or its alias. In coarse grain reduction modes, after the load dependency builder, we go directly to the reducer part. And at the end of the load dependency builder, we construct the list of all used modules inside the application. The call graph builder detects use exported functions for each use modules, and note that the call graph builder is called only during the fine-grained reductions. It traverses the modules ASTs and records imported modules member expressions, basically which functions or variable that was exported is used by other modules, mark used unused nodes of the AST, and as I said previously, it runs only during the fine-grained reductions. The reducer is responsible for removal of unused files and functions. It removes the unused nodes from AST and generates the JavaScript code from AST using also well-known library called ESCodeGen. On this slide, you can see the MININODE reduction validation experiment pipeline. So to be sure that the MININODE is not breaking any kind of intended functionality and then reducing the code base, we decide to validate it using the experiment. So in this validation experiment, there is main 5 steps: filtering and data collection, installation and testing, application reduction and reduction testing, and then analysis part. We will discuss next couple slides each of those in more details. The first step was filtering and data collections. From all of the packages that we have inside the npm, we selected, during the filtering and data collection step, we selected all the packages from all the packages from npm. We selected the package which had the dependencies, unit test dependencies, such as NYC, Istanbul, and others. We also selected the unit tests for which we can automatically calculate the unit test coverage, because it's also one of the important measurement. So we wanted to make sure that the package that we're selecting have the full coverage. And also we retrieved all the code from the GitHub, because not all of the developers ship the packages with the tests. So the next step was to install the original version of the applications and run the unit test, and filter out also the applications that even without reduction, the unit test is not passing. So the next step was application reduction itself. So we run the both coarse-grained and fine-grained reduction on initial production version of the applications. And then we validated that the reduced versions actually can pass all the unit tests without any kind of errors. So this theoretically will prove that the unit test was not broken, and our reduced version is so MININODE didn't break any original behavior. So this is the validation results. In total, we tested 37K packages. Coarse-grained and fine-grained reduction succeeded in 96 and 95% of the cases respectively. Here in the table, you can see how many files was removed, lines of logical code, and the number of removed exports. We also validate that we are removing the access, restricting the access to the file system and network module. After validating the MININODE, we run the large-scale Npm experiment. The goal of this experiment to measure the attack surface of all Npm packages. So the large-scale experiment consists of 4 steps. In the first step, we gather all the Npm packages. On the second step, we install the production version of the packages and then reduce them. In the third step, we run a vulnerability analysis of the packages. Then in the final step, we analyze our reduction results. Overall, we were able to successfully process 672,000 packages out of more than 1 million packages. On average, packages declared almost 2, but installed 27.3 dependencies, which is almost 14 times more installations than declared dependencies. And almost 18% of all the packages have at least one vulnerable dependency, according to Snyk database. So on the right-hand side table, you can see the reasons why we couldn't process all the 1 million packages. So the main reasons were missing the entry point for the 88,000 packages, which means the package didn't declare any kind of entry point and the MININODE couldn't find it. Another reason is we couldn't resolve the value statically. We couldn't resolve statically the value for the dynamic import. So if we find any kind of dynamic import that we cannot statically resolve, basically we say that, okay, we cannot reduce this package without breaking it. So we have 128,000 cases. Also, another reason was that the installation was failing for the 26,000. It was due to the different operating systems and other reasons. And for the 20,000 cases, the package itself was not written using the Commonjs convention. For example, they were using the different languages. For example, they were shipping the JSON file, or they were shipping the CSS files, and so on. And we have other small minor issues. So here's the reduction result of the large-scale experiments. So in total, we were able to remove 79% of the all JavaScript files that was shipped during the installations. we were able to remove the 90% of the logical lines of code and remove almost 90% of the all exported functionalities. We're able to also restrict the access to the built-in file system modules in the 81 cases, 81% of the of all applications, and restrict the network built-in module for the 92% of the all applications. So this was the results. We also analyzed the vulnerability reduction results. So here you can see the top 10 vulnerability categories and vulnerability removal results. The column partially removed and fully removed, it means different things. So for the partially removed, it means, for example, for the arbitrary code injections, we were able to, for example, if the one application is dependent on two vulnerable dependencies from the same category arbitrary code injection, but we removed only one of it, we count it as an partially removed. And for the fully removed, it means if we were able to remove all the vulnerabilities from the same category from the arbitrary code injection. So those are results. So as you can see, for example, for the arbitrary code injection vulnerabilities, we were able to fully remove for the 47% of the cases. So in conclusion, we developed a system that can automatically reduce the attack surface of Node.js applications by removing unused code parts. In addition to this, we analyzed the 672,000 Node.js applications from Npm repository and measured the attack surface. And then we created a custom build of Node.js that can restrict the access to built-in modules using a whitelist generated by MININODE. Thank you. And